Hi, Garima. Good evening. Am I audible?
Yes, ma'am, you're audible.
Okay. Okay, so for today's session, we will be covering a new library, which is a white box toolbox, uh, which comes within Python only. And using that white box tool, we will be seeing that how to perform hydrological based terrain analysis. And we'll be using only one dataset, which is a DEM dataset. And using that DEM dataset, we'll try to perform all kinds of terrain based hydrological analysis that one needs to do for multiple use cases, such as urban planning or simulations, or for creating flood vulnerability indices. So for all those tasks, one can use Whitebox library. But before jumping into the library itself, uh, I will do a little brief on the what hydrological analysis is, and we'll see like few concepts as well before doing the demo of that. I'll not go into very much detail about each of the processes, but I'll brief and you can just go through that so that you have all and understanding of all the terminologies before you perform these exercises. So few concepts that you must need before performing this exercise will be to understand what is terrain analysis, what is DEM, what are streams, stream order, flow accumulation, flow direction, watershed, and basins. So, basins and watershed will be covering in the next session. For this particular session, our objective will be to first understand the concept of what digital elevation model is, how one can download and get this data freely from multiple sources, and then we'll learn how terrain control the surface water flow and drainage patterns, and how why people actually use them to generate and study the water flows within a city or within any kind of a study area that you may choose. Then we'll be performing some pre-processing steps, which are called as hydrological pre-processing steps, called a sink filling, depression removal within the DEM as well, and why they are necessary, and to understand why these particular steps are necessary for performing hydrological and flow modeling. Then another term will be to understand what is flow direction, why one should do the flow direction, and what you get at the end once you perform flow direction. Then similarly, we'll generate a flow accumulation raster as well. And then using flow accumulation raster, we'll understand how accumulation identify potential drainage paths and river channels within any study area. Post that, we'll be extracting stream networks, and that network will be generated on the basis of threshold based analysis on that flow accumulation raster that we will be delineating using the DEM file. And then after that, we'll be identifying where the streams and the river channels are originated with that same DEM satellite data that we have. And then the in this particular step, we'll get the output in a raster file. So we'll be converting them into a vector file as well, so that you get the stream orders and everything. We'll also understand what stream order is and what is the significance of stream order when you are working to study about the flow analysis and the hydrological analysis. Then we'll try to optimize the stream network for visualization, because since these files can be heavy files, so in order to use them for the visualization for result generation, you need to make them into such kind of formats so that's it easier and lightweight for visualization and for different other purposes. At last, after creating every step, after creating every raster and outputs, we will be also like just to visualize and see what outputs we are getting in at every step. We'll be using attribute based styling systems, and we'll be styling and visualizing in terms of plot, and also using interactive tools like leaf map and folium library. So we will be visualizing all the hydrological outputs, overlaying raster and vector data. Same comes under visualizing only. Then we'll build an interactive map, which will contain base map, flow accumulation layer, stream order network, custom legends, layer control. So this will be the agenda for this particular exercise. And for performing this exercise, we will be focusing on the white box toolbox, which comes with Python only. So a little brief PPT I have created to make you understand what terrain-based hydrological analysis is, and this is one of the like a very I would say that a lot of people perform these hydrological analysis. So if you are like if you know how to perform hydrological analysis using Python and you know all the basic terminologies and everything, so like you are on the we are on the very good page that you know all these things. So these concepts are important. So first thing is digital elevation model. So what digital elevation model is, it is just seems like a raster file. It will be in the .tiff format only. The only difference will be, let's suppose we had NDVI and other raster files. There we had the value of vegetation index and all those things. Whereas in a DEM-TIFF file, we will have in every single pixel, we will have the value of elevation in any of the area. So there are multiple things like DEM, DTM, and DSM. So DEM is the digital elevation model, DTM is the digital terrain model, and DSM is the digital surface model. So everything is different from each other. So I would request that go and study the difference between all three things first, and then try to perform the analysis using digital elevation model. Then you'll get better understanding why we choose digital elevation model for hydrological analysis. So this is a question for you all. So a DEM is a regular grid of elevation value where the Z value means the pixel value is representing the Earth surface. That in a Earth, that Earth surface is how much it is elevated from the mean sea level, and then every single pixel will is a resolution means cell size. It will control the detail and the scale of the analysis, like at what height that digital elevation model is taken from the satellite. Then higher the resolution captures, finer will be the terrain features. So means higher resolution capture means that the image is taken from the satellite at a very lower height. That's why you are getting more finer terrain features. If you are taking the image of the earth from a very high height, and then at that level there will be lower resolution of your DEM file, that means you are capturing less finer details of your terrain features. So that is what resolution means in terms of digital elevation model. So common source can be LiDAR, DEM, SRTM, and Copernicus DEM. And the DEM that we will be using, that I have downloaded from USGS, it is the SRTM DEM only, which I have downloaded. You can also download from USGS itself. This is the website, USGS Earth Explorer. The, from here only, you can choose the product as SRTM DEM, 1 arc angle, and then you can download. So I have already shared the DEM data in the previous exercise, so you can use the same for this exercise as well. So the first pre-processing step that people or we perform whenever we are doing hydrological study is the sink filling. So what do you mean by sink filling? Is basically that you are removing any kind of depressions to ensure continuous downslope flow and hydrological corrected DEM. Means, let's suppose you had DEM values, but for some reasons you have very spark difference between those DEM values. So what it will do, let's suppose this is a continuous DEM raster file, so it will have a continuous value, whereas these blue points are the sinks. Like here, maybe the value is in very negative or very positive. So they are the depression which will cause errors when you will further try to delineate the river flow or the channel flow. So maybe it will treat it as a pond and something if you do not treat these depressions right now. So what we do sink fill them. So it average out the values by choosing the nearby pixel, and then it fills the dem value. So now what we'll do, now your dem will be like a continuous downslope will be there. So I hope that it is cleared from the image that here if you see that if the water is flowing or if the surface is flowing like this, so the arrow is going because here there is a lot of sink present. Here it's like a pit that is created within your file. So once you have filled this particular pit, now it is a continuous downward flow is present within your dim file. So it is like we are correcting this particular voids that are present within our surfaces, so that now we have a proper actual levels or actual elevations of surfaces present, which we will be using for further finding out the actual flow of the rivers or the channels or the water flow or the drainage pattern of any of the study area. So the goal why we do sink filling is to remove artificial depressions to allow continuous downslope drainage. Why we mentioned like artificial depressions? Because they are not the actual elevation values that are present in any of the data. They might be created due to the wrong reading while taking the images from the satellite. So at that level, they might be a error values. So that's why we are rectifying that. So fixes artifacts from noise. Noise means simple noise during taking when you are taking the image from a satellite. At that time, there was some noise in the sensors or something. That's why this depression is created. Vegetation, voids, and mosaicing. Mosaicing seems means yesterday we discussed about mosaicing. So let's suppose like we do the mosaicing of the files and in the same manner when you are downloading this dem file from the USGS, so USGS also performs some kind of pre-processing methods before it is giving you the product to download. So dem is kind of a product that they are making from the raw images that they took from the satellites. So this is kind of a product that they have created after performing few steps. So there might be a possibility that while they are performing some kind of steps in between, there might be some errors, and because of that, there are wrong values present in your data. So that is the reason we perform all these steps. So output, what this will give you, it will give you a hydrologically corrected dem ready for flow modeling. So this particular step we perform when we want to do a flow modeling from our data. Okay. So the next step that we will be performing will be a flow direction. So what flow direction means? Flow direction, for calculating the flow direction, there is a concept called D8 algorithm. I'm not going into the details of the D8 algorithm. You should go and read about it. But this is the algorithm that is generally used by people for calculating. This is like widely accepted algorithm, which people prefer to find out the flow directions from the dem data. How actually it works? So basically what it goes into 3 by 3 window, elevation, gradient average, and chooses D8 direction. Means let's suppose you have all these kinds of pixel here, and this is the pixel, and you have to decide that in which direction now my water will flow. So what it will do, it will check the elevation of all the pixel that are around that particular target pixel, and then whatever will be the lowest value in all those pixel, it will decide that my water will flow into this direction. Why? Because this is the lowest elevation value, so obviously water will drain into the side where there is a lowest elevation. The same thing it is mentioned here. Each cell drains to its steepest downslope neighbor among 8 surrounding cells. So if you are talking about this cell, so it will look into the 8 surrounding cells, and after that it will choose the lowest elevation value and decide that this is my downslope um, direction. So that is what we get. So when we calculate flow direction, at that time if you try to visualize the output, so you will see the arrows. So it will make arrows in your whole data set, and that arrows will define that where the water is actually flowing within your study area. So since flow direction is it like specifically flow direction is not really useful, but we will use flow direction to delineate other factors. I'll show you what other factors, like for calculating the stream orders, for calculating the streams, you will need a flow direction output. So flow direction itself is not really important, but this particular step is important for our further step, because this will decide that in which direction the water is flowing, and how it decide on the basis of D8 algorithm by checking the elevations of its 8 neighbor cells. So requires a hydrologically corrected sink fill dam. So you can relate that why we need to do a sink filling, because if we don't do a sink filling, so let's imagine here there is a sink in this particular pixel, and its value is like very less, maybe 10. So it can be a wrong representation, right? So that's why it's important that we are only using sink fill dam for performing flow direction and everything. Now the flow accumulation. So for calculating the flow accumulation, what flow accumulation will give? It will give you count the upstream contributing cell per location. Means for, let's suppose you are targeting to this particular pixel, this yellow pixel. So what it will see the upstream cells, upstream pixels. What do I mean when I say upstreams? Means the higher elevation pixels from that particular location. It will count them and it will create a kind of a trace. It will trace those values, like how it is going from high to low. So as you can see that flow accumulation, so it is going from here high to low. So if here the flow accumulation is higher, that means it is kind of a valley. It is kind of a potential river channel where water is getting stored. So from this direction, water is coming and getting stored into this. So high value traces, valleys, and potential river channels. So where there will be a higher value for the flow accumulation, so that area will represent that there can be a river channel, or there can be a water body, or a water is accumulated in this particular area. That's why we are calling that this step is a flow accumulation step. It will show you that here water is getting accumulated. So that is what the meaning of flow accumulation. And important thing, while you are visualizing the flow accumulation, we should always use log scale. Log scale means logarithmic scaling, means exponentially what we will do, since the values of flow accumulation varies from 0 to 1 million value. So the difference between the values is very large. So if we do not scale it and we do not perform logarithmic algorithm into our data, so what it will do, it will expand everything into a very large scale, and you will not be able to like discriminate between where my channel or where my river is forming. So in order to do that, we scale it down, and when we scale it down, it will just highlight my rivers in a better way. So using log scaling is important when you are doing the visualization of your flow accumulation. For that purpose only it is necessary. Otherwise, you can just use the raw values of flow accumulation. Next, once you have the flow accumulation data, we will be using flow accumulation data to delineate the channels. Obviously, the flow accumulation will be like this. It will only highlight the pixels where there is more flow is accumulating in that particular area. But now we want the exact line, means we want the exact line of the rivers so that we can identify the streams. Streams means you can imagine that a river is flowing. So if you want a line, so for getting that line, we do stream network extraction. So for extracting the stream network, we give flow accumulation raster and we apply a threshold. I'll explain about the threshold when we'll do a hands-on. So we apply a threshold, and on the basis of threshold, it will delineate the boundaries or the streams into your data set. So now you will get a channels into your whole data, and then simply tune that threshold by terrain, climate, and DEM resolution to avoid over and under extraction. So we'll talk about the threshold, why we actually do the thresholding. And then once you get that stream network, the output will be in the raster file. Then we'll convert it into the vector file so that we can further actually get the like a line geometry from the streams, and then it is better to visualize and study and everything. Another important concept is stream order. You will see that every single stream will be auto allotted with the order. So, what do I mean when I say order? So, higher the order, higher the flow accumulation, and like it major the tributary it is. So if you know about the tributaries in terms of if you have studied about the rivers and everything, so the main channel is our river. Then from the rivers the branches get cut, and we create a smaller rivers. So that is how the hierarchy is built for the rivers when we talk about it. So that is what mean by orders. So order will define higher the order, higher the velocity, or the not velocity, higher the flow accumulation will be there in that particular channel, means that is the major tributary. And as the number goes lower, means as the order is getting reduced, that means that the tributaries are getting reduced to the like a narrower channels or the smaller tributaries like that. So that is what do you mean by orders. So when you are converting your stream raster to a vector, it will auto generate the order column as well. And from that order column, we can actually delineate that, okay, let's suppose there are 6 orders generated into your file. So if you want to just delineate the major rivers only, so my major rivers will be only the higher order. So let's suppose 6 are created. So 6 and 5 are my major rivers. Rest of my are smaller and narrower channels are present. And I want to delineate or like reduce my whole data to only major rivers. So what I'll do, I'll just extract the data from my data set to only 5 and 6 orders so that I can like plot or I can perform analysis or I can get an idea. Okay, fine. These are the major river channels are present in my study area. So that is what the importance of stream order is. So as I explained, this was the stream order. So let's suppose this was the main channel, higher order 3, and then it has branches out to the smaller tributary, the second, and then it again branches out to the smaller tributary, which is 1 order. So the order of this particular, the main channel will be 3, then the branches will be 2, and then further if it branches out into the smaller channel, it will be 1. So like this only, it will capture river hierarchy, supports scalable symbology and watershed analysis. We'll talk about watershed later on. So we'll stick to river hierarchy and scalable symbology for now. So it because orders will help you define how my river hierarchy is built. Like in your study area, you will be able to define that, okay, fine, these are the main river channels, these are the smaller river channels, and then support scalable symbology. Since you have the orders defined as a column, you can use that column for attribute based styling so that you can have different colors for different uh, orders. So that was the meaning of stream orders here. Optimization, we'll talk about that. So for optimization, what I'm doing when you are converting the streams from this raster based pixel to a single line, what it will do, it will create multiple segments, like thousands and 2 thousands of segments, because it will create every single small uh, if, let's suppose this is that, so it will create a lot of segments into the whole data. So it is not actually possible to plot everything. Otherwise, let's suppose you have 1,000 rows in your data set, in your data frame. So it will take a lot of time to display, to visualize, to present, to deduce any information. So what we'll do, we'll dissolve this. We'll use the dissolve tool and we'll dissolve the similar order of tributaries into a single geometry. So once we are doing that, we are just optimizing. You can see that before it was a fragmented segments. So every single segment, it was different segments, but the order is same for all these things. So what we did, we just used the dissolve tool, and when we dissolved, so like this become a single geometry, this become a single, this become a single. So now instead of a fragmented segments, you have a simplified, better single geometry. So now when you are processing it, it's easier to visualize and everything. That is what I meant by attribute based styling. Like order wise, you can define, you will be able to visualize, okay, fine. This is the dark color, so it is order 4, order 3, order 2, order 1. So as the order is decreasing, that means the hierarchy of the river or the flow accumulation is getting decrease in my channels. Then same, we'll visualize it, and this is what it means by overlay. We will see by overlaying the flow accommodation and streams together so that we can see that, okay, it is also matching with my flow accommodation as well. So this is just to generate more insights and everything. Okay, now this was it for the theoretical part. To get more into this, I will recommend that you should read about all these concepts that we just discussed to know what they all mean. Now we'll directly go to the hands-on. So first thing first, uh, we will be downloading the local tile server because I'll be using Leafmap for plotting. So we will download, install local tile server. I'll just run this again. Then I'll install Whitebox library and Leafmap library. Whitebox because Whitebox is the toolbox that I'll be using for hydrological modeling studies, because there are few tools that Whitebox will directly give you for doing these kinds of analysis. You don't need to perform steps. They are already inbuilt with the Whitebox. Once it is installed, we will import Whitebox and Leafmap. By the way, any questions in this before I move on?
No, ma'am.
Okay. So what's the status like? Do you guys already know about all these concepts, or like it's new for you?
Ma'am, not these topics are not new to me.
Okay. So then that's good. What about others?
Yeah, this is not new for me.
Okay. Nice. So once we download everything, install everything, we'll import the Whitebox and Leafmap. And then what Whitebox will give you, it also you an option to like define the directory, so that every time when you are using the Whitebox toolbox, you don't need to specifically define the whole path. So what I did, I created a folder for my project within my drive. So within demo data, I have the folder called Whitebox demo. Inside that, I had my file, which I want to use for my study for this particular session. So I set this folder as my working directory. So what it will help you, that whenever you want to write any file, whenever you want to like fetch the data from this directory, while you are using the Whitebox, you don't need to define the whole path again and again. You can just write the file name. It will directly link it to that particular path because we have already set the working directory. This particular line here, we are initializing the Whitebox toolbox. This is not just a package like we used to use other packages like Python, NumPy and Pandas and GeoPandas. This is a complete toolbox which is specifically designed for hydrological based analysis. So whitebox tools, this will initialize this tool. That means it is ready to use. And then we have also set the working directory. So wbt is just a variable name. You can define the name however you want to. Dot set working directory, define the path of the folder where you have the data and everything. We'll run this also. Now, what WT also provides you with, let's suppose for other libraries, you need to specifically go into uh, their official websites to know more about that library. Whereas dot list underscore tools, it will give you a list of all the tools that are available within WT toolbox. So it is very handy and very useful. You can just look into this. So it will always give you a tool name, and then it will give you why this particular tool is getting used. So everything you can like read from here. Just run this, and then you will get all the information that are present within this, so that you can now study from this. Like unnest basin, extract whole watershed for a set of outlet points, unsharp masking and image sharpening technique that enhance edges. Like it will give you a basic one-liner why this particular tool is getting used and what is the use. You can also see it provide you wetness index. You can directly use the key as wetness index and calculate the wetness index, weighted sum as well, perform a weighted sum overlay on multiple image raster. So it also helps you with AHP analysis, like weighted overlay analysis that we used to do. So it has multiple tool present within it. You can explore this particular toolbox like this, that what all is present in this like this. You don't need to go anywhere to search that what is available in this. So whatever is inside this, you can obviously use and perform analysis. Okay. Now we'll move to our very first step, that was to fill the sinks. So fill depression, WBT was the name of the variable where we initialize the white box toolbox. The name of the function is fill underscore depressions. So it will need only one input from your side, like what's your file name. So you can see that I have defined only the name of the file because the path I have already defined within the white box. Then in the output, I have defined filled underscore dem, like what should be the name of the file where I want to save it after doing the fill depression analysis. So I'll run this also. It will take a little bit time and then it will save it. Then to generate the flow direction, the tool is to d8 underscore pointer. What d8 underscore will pointer will do? It will create a flow direction as I have shown you in the PPT. For that as well, you need a input file. That input file will be a fill dem raster, not the original raster. And then we'll define a name of the output file after calculating the flow direction. So d8 pointer method we are using to calculate this. Let's suppose you don't know that what should be the output, what should be the name of the key. So you can just hover over the function and it will just tell you that what you should give. So dem means dem file it needs, then output parameter it needs, and you can make it false, callback none, and it has also defined everything, like what all these things means. So even if you don't know about the function, you can just explore according to in this. So okay, we calculated the flow direction. Now, just by hovering over the function also, you can get the help. Also, white box also provides you a help by the function dot tool underscore help, and you can write the name of the function and it will give you that what all that function needs, like how you want to define the input, how the output should be. So you can see that I have run wbt dot tool underscore help and then the name of the function. So I wanted to know that how to calculate the flow accumulation and what all should I give within the flow accumulation in order to calculate. I don't know for right now. So I'll just run this tool. So it will define and describe everything. So in the description, if you go, you can see that it needs an input, and input should be with the key as I. So input raster dem or d8 pointer file means both output can be given to this. Either input is your dem file or your d8 pointer file, means d8 pointer file is the flow direction file. Then output raster file you should give as output type in this. You can see that here input is given as I. Then output means in what file you want to save the output. Then output type also you need to define. And what should be the output type? So one of cells default or the catchment area and specific contributing area. So there are a lot of type of output how you want to, but generally we use cells only because we want it as a raster file only. So we'll use out type as cells. In input, we have given our filled dem file, like the dem file. We haven't given the D8 pointer, but you can also give the D8 pointer file as well. Okay. So these three steps are done. We calculated the flow direction, flow accumulation, and we have filled the sink as well. Now we'll go to the visualization part. So I have used leaf map only. This I wanted to have the raster loaded, the flow accumulation that I calculated. So we have saved it as flow accumulation.tif. So the path of the file we will give, the layer name, I want to show, and the color map, what color map I want to give. So you can see that it looks something like this. Wait a minute, it is getting loaded. Okay, so these dots, the different color dots rather than blue, if you can see here. So these are the flow accumulation channels. Basically, it is showing that only. So this is how now flow accumulation will look like. That within my whole raster, these can be the tributaries or the river or the flow of the water will be in my raster. And I have also plotted it using the matplotlib as well. And in this, while I was doing the plotting, so I used the logarithmic scale that I told you. So before I just opened the data using Rasterio. So before doing the actual plotting, when I was showing and defining the color map, I gave that your data, what we loaded here, np dot it comes from the numpy library np dot log1p. So we have just converted the whole data using that so that we are scaled it properly. Now you can see that it is better visible. Can you see in the screen? Is it visible? The tributaries are better visualized in this, like this. Is it visible to you all?
Yes, ma'am.
Okay. So that's how you can also plot these results and like represent if you're doing any kind of project, either using interactive map or using the normal matplotlib.py plot. Then next step is the stream networks. Within stream networks, there are the input file will be the flow accumulation raster, and the key will be the flow accumulation is equals to, and we'll define the TIFF file. So this will be the TIFF file that goes as input. We'll define the name of the output file, and then obviously we'll define the threshold. So why we define the threshold? Now that you know, can you anybody answer? What will change if I reduce this threshold? Alicia? Anybody else? Yes, no, you can just Let me know even if you don't remember. I am waiting. Anybody answering? Why we use threshold?
Don't remember, ma'am.
Sorry, Veena, what you said?
I don't remember, ma'am.
Okay. Anybody else? So what threshold will do basically, if you'll make the threshold as very small, so what it will do, it will include all the small tributaries. There will be a lot of tributaries present within your streams. Whereas if we put the threshold value as higher value, so it will only consider the major rivers only. Because what threshold basically do, it will just make sure that when you are basically computing your flow accumulation data, so every cell will be representing some kind of a value. So wherever there will be even a very very small flow will be accumulated in any of the area, so it will consider that as well as a stream or as a channel. So to basically delete or remove those kind of very very small channels or small flow accumulated areas from our streams, we use the threshold value. So it we will decide the threshold value on the basis of how many tributaries we want in our output and at what scale I want to like the generate the streams and the stream orders. And do we want to work with every smaller streams? Let's suppose if somebody is studying the urban floods, so they will be using the smaller threshold value because they have to read or study about the tributaries or the channels within the cities which are very very small as well. So in that case you will be using the smaller threshold value. Whereas if you are only considering about the flood level analysis, city level analysis, where you only concerned with the major channels or the major tributaries present within the cities, not very smaller and narrower channels, in those cases you will define the threshold as a higher value. So for now we'll be using 1000 threshold because the lower will be the threshold value, more will be the streams that we will be generating. So WBT dot extract underscore streams is the function that one we use to extract the streams, and the output will be a raster file from here. To optimize this, we will be converting it to a vector data. So while we are converting it into a vector data, we'll be using the function name raster underscore streams to vector. So there is a specific function for converting raster to vector for streams. Why? Because there is a different algorithm that goes behind converting the streams into a vector. It is not a normal raster to vector conversion that you just took a raster file and converted into a vector, because here we need to consider the orders, the flow accumulation values, and all those things. On the basis of that only, it will generate your vector file and it will create a new column where you will have the stream order value as well. So that's why we will be using the specific function of raster to vector conversion when we are dealing with streams. So that function name is raster streams to vector. They need two data set as a input. One is the stream file. So we will define the stream file. Another is the flow direction file. Now for stream to vector conversion, we need a flow direction defined, not the flow accumulation one. Why we need flow direction here, not the flow accumulation? The same reason, because the flow direction will give you the actual arrows direction that where my water is flowing. So on the basis of where your water is flowing for every single smaller pixel and for every single segment, like flow direction will give you the direction in the north, south, or east for every single pixel. So on the basis of that only, when you are converting it into a vector file, it will create a new column called as stream order. So the stream order, like is it a fourth order, third order, will be decided on the basis of flow direction only. So that is the reason we are defining the D8 PNTR file as a input into our vector conversion. Then output, this will be a shapefile conversion because I want it as a vector file. So I have defined the extension as .shp here. Now we'll visualize these streams as well. So you can just see that same mleafmap.map initializes the map. Then first we needed to add the raster. I added my actual dem file. Then I needed to add flow accumulation.tiff file. Then I wanted to add my streams as well. So right now I'm adding my stream, not the output that I got after the vector conversion. I'm just plotting the streams. So that's why it has no order differentiation. So if I just, we'll just run this. So here it is more visible. So you can see that this was the main channel. Like it is highlighted in yellow. This is the main channel. And right now we haven't yet dissolved. So you can see that if I'm just hovering over this, it is highlighting every single small segments. It still, it is not dissolved into the single geometries. So every single segment are different when I'm just hovering over this. And if I just show you one more thing. I'll show this later. It is taking a lot of time. Okay. So the streams that we calculated, the one that we converted from raster to a vector file. So it was saved as a streams.shp. So we will open that particular file using the GeoPandas because I want to see that what all is present and what is the order and everything in that particular file. So you can see that it has created a column called strm underscore value, and it is still 1111 present in the whole data. And just to check, just a minute. And since right now we have only loaded the heads only, so I wanted to know that what all unique values are present in this particular data in the strm column. So you can only see that it is showing that there is only one value present. So I mentioned that there will be orders. So the problem here is that we still haven't calculated the stream orders. It has only we have only converted it from raster to vector, and while we are converting it from raster to vector, it has just allotted everything as order 1 because there is nothing that we specified to calculate the order and everything. So there is another function that we will use to calculate the stream order. Before that, let's suppose you want to just plot this stream only. So by just plotting as well, first I showed you how to visualize it there in terms of interactive map. And this is if you want to plot it using matplotlib. So streams.plot, you will define the column like by using which column you want to define the tributary and everything. So we have defined the column as well. If you want to give by the attribute based filter, then the color map that you want to define, and then here line width is equals to streams is equals to width, means we can also define the width, that how much thickness you want in your stream, so that you can define using the line width. So streams width, because we have changed the width here, that fetch the SRTM value and multiply it by 0.5. Why we did that? Because let's suppose if there are multiple orders present in our stream, so it will give a different thickness value to different stream orders, so that it is visually, you are able to distinguish between different kind of stream orders. But since right now there are no order present in this data, so do not confuse. So that's why I put this, that once you are just converting into the stream, you will get a column called as a SRTM value, which may be seems like that it is a stream order value. So it is a stream order value, but till now it is only considering everything as a like a major tributary, and there is only one tributary. To actually delineate the order and everything, now there is another function which is called as the stream order function, and there we will define again two inputs. Now we'll define the stream TIFF and also we will define the flow direction TIFF. So we will get the order. Earlier when we calculated the streams, we just normally converted into a vector file here. But here, just a minute. For calculating it as a stream order, so this you can perform this step if you just want to visualize and you really don't want orders and everything, and you just want to show that tributaries maybe, that's it. But you specifically, if you want stream order, then you will use this particular function, and you'll again pass the flow direction and the stream TIFF files and save it as the output. So this I have saved as stream order TIFF here. And then again, I have converted that stream order that I've calculated using this new function into a normal shapefile, raster to vector. Now we will read that stream order file. And now in this head, if you just see that it is showing the STRM value as 1 and 2 also. And we'll check the unique also. So in unique, we get 1, 2, 3, 4, 5, 6. So that means there are 6 orders of stream that are present within my dataset. So now you get the unique values from your data here. Now comes the important part, which I told, that still you have different tributaries present. Like there are a lot of segment for single order value as well. So now what we'll do, we'll dissolve all these tributary geometries by using the order value. Let's suppose they are only categorical only. There are only 6 order values. So what we'll do, we'll dissolve the geometries by using this STRM value. So streams underscore order is the name of the geodata frame that we created after reading the file. Dot dissolve, the function that we will use to merge the geometries. Then how you want to dissolve it. This is same like dissolving the buffer. So creating a single geometry. So it is like by using this particular column. So what it will do in the background, it will group all the rows which will have a common column, and then it will merge into a single particular geometry. So instead of having like 1,000 rows, you will only get 6 rows for every single, like you'll only get 6 rows, and every single row will define a single order value. This reset index line is just for the, like, for doing the safe side, that you have reset the index and now the index are coming as proper. If I just comment this and I just run this, so you can see that there is no indexing as such present in our data. So when we deal with geospatial data, indexing is very important. So that's why for the safe side, we run a tool called dot reset index. So it has created an index for your rows within your data. So now you can see that I haven't done head also. We got these 6 rows. So that means there are only 6 rows present within our data now, instead of lot of data that we had in. Let's suppose I don't do dot head in this. You can see there are 7132 rows present in our data. So it is too heavy if we go and like load it, visualize it, plot it, or perform any exercise onto this. So that is why when we just reduced our whole data frame into 6 rows only, and it is the correct representation of our data also. Then now simply what we'll do, we'll now plot it. Now you will be able to see different colors for different tributaries, so that you can now visualize that which is the main tributary that you have, or the main channel in terms of order. So again, for giving the width as well, there are 2 ways to give it. Either you just define it here only, streams. Within stream, just define the column name and multiply it by any kind of constant. Why I'm multiplying it? So let's suppose the stream order is 1. So for one order, the value will be 1 into 0.7. If value is 1, 2, so it will be 2 into 0.7. So that accordingly, there will be 6 width values as well. And by that, it will assign a width to every single tributaries like this. You can just see that the yellow one is have a higher thickness value compared to the other ones. So that is how it looks visually more good and appealing like that. Another way is to just fetch the width here, stream order, add a new column as width, and then in that particular column you are just calculating the new column using the strm value column, and then here you are passing the width column. So that is one way. Or another is you can directly perform the calculation here itself. We have passed a column, that by which column you want to plot. We have passed the color map. Then we pass the width thickness, because on the basis of thickness, it will look more good in terms of visualization. If you don't define this thickness, the thickness will be same for all the tributaries, only the color will be different. But if you define the thickness, so it will be like defined on the basis of that. Legend true, that is why you are getting the color map on this side. Okay. So I mentioned here as well, order 1 means small tributary. Higher the order, your hierarchy of the river channel will be higher, like that. So in this, we plotted the stream order. So it looks like this. In this, we plotted the dissolved. So you can see that the output is same in both the things, is just the difference of the time. Like your process is more optimized when you are using the dissolved one rather than using just the undissolved data frame for plotting. Okay, this is same. Now, how you can, I told you about filtering the major rivers. So how you can filter it. So let's suppose in the stream dissolve, we have 6 rows present in that. And higher the order, higher will be the river channel. So let's suppose we assume that the stream value or the order which are greater or equals to 5, that are main channels or major river. So you can just filter it like this. So stream dissolved, your data frame name, you have defined the column greater or equals to your operators, and then you have fetched into stream dissolve. So it has given you only those values which are greater than or equal to 5 in the SRTM column. So If we run this, now you can see instead of 6 column, now we only have 2 columns here present. Okay, so we are skipping this for now. This I have written. Let's suppose you want to specifically define any color. So what you can do in this data frame, you can add a new column. In that new column as a list, you can add the new two values for those two columns. Let's suppose the color hex code you can add. And then if you want to fetch that exact hex code for your two stream orders, so you can fetch by that column. So but for that you need to define the key as color while you are plotting. So color is equals to major river, and then you will pick the column as name as color where you have specifically defined the color name and everything, and rest everything will be same. Like here while we were plotting in this also, if I'll just comment this for now. Here, as you can see that I am defining the column as strm value, that on the basis of strm value, just define the color map on your own choice. So it will assign the color on the basis of the color ramp only. We are just defining the width. But let's suppose you have the colors and you specifically want those colors only for your 6 orders. So what you can do, you can just add the one new column in your data frame, write the hex code on those columns, and then if you want to map on the basis of the exactly defined columns for the color that you have, then you can just write it like this. Instead of color ramp cmap and the name of the column, you can define the color is equals to stream order and then define the column name as color. So you can plot it like that also. Okay. Next, this was the, let's suppose I filtered this major rivers. So now we are plotting this. So instead of all the tributaries, now you are only able to see these tributaries only, which are greater than 0 and 5. So only 2 tributaries are visible in this. If I increase the thickness from here, you can see that it is more visible now. If I just keep on increasing, it looks something like this. It looks odd. So we'll keep it to only. So this is how it looks. Uh, Now the last thing which is left is same thing. I just tried to visualize these things. These were the plots, but if you want to plot these stream orders on the basis of attribute styling use in the interactive map, so you cannot just use leaf map. Why? Because leaf map is not very compatible with attribute based styling. It will only allot a single color. You will not be able to assign attribute based styling on a line string, though the sometimes it's able to assign in a point and a polygon data, whereas with multi-line string it creates a lot of issues. So what we'll do, we'll just club the leaf map in the folium library to uh, to have the color within our data. Okay, so we will leave it till here only. It is still incomplete. We'll do the interactive mapping of these outputs tomorrow. But instead of that, we have completed till flow accumulation, calculation, stream order, and everything. The only thing that is left is just to visualize it in that. I can show you here, but I'll not be able to run it. I'll share by correcting. There's something wrong with this code right now. I'll explain it tomorrow. But when you visualize it, it will look something like this. You can see that the order wise color and the streams are visible here, and you can see that here there is a major river as well going on. So we can validate as well using the base map that the yellow one was the major tributary and these were the branches, the smaller ones were there. They are going from the city side. So this was the main river that was going by the Delhi area. So this is, I guess, Yamuna only, right? Yes. So that's why this yellow one is the major river tributary. So we have validated as well from the original satellite imageries. And if you just try to visualize in the flow accumulation raster as well, so in that also you can see that we had the tributary there only, and it is very highlighted as the major tributary. So this is the complete workflow, how you can delineate all these things. So only now the watershed and the basing calculation is left. We'll do that tomorrow. Okay. I'll share this PDF for this code as well. So try to practice it. Any questions in this? Anybody?
No, ma'am.
Okay, then we'll close this for today. And good night, everybody.